In the last segment, we saw how to use our solubility table to do some math to figure out the extent to which we can get solutes to dissolve. We figured 222 grams of water. If you don't like grams of water, remember the density is essentially 1.00 grams per milliliter. So 222 grams would be equivalent to 222 milliliters. Segment 7 begins on page 17 with a question about generalities. And the question is, why do fish marine life die at heat discharge sites at lakes, rivers, and streams? Well, it's because the solubility of oxygen decreases when temperature increases. And that's why you have dead zones in lakes, rivers, streams, and the oceans. And that's another reason why increasing the temperature of our water supply is not a good thing at all. Manufacturing is a big source of that. Why does soda go flat when it sits out at room temperature? Again, solubility of CO2, that's what makes the soda fizz, decreases when temperature increases. Okay, so again, you can quantitate this just like you do for ionic compounds, but in general, what we're going to want to know about gases is that solubility of gases decreases when temperature increases. Okay, other properties of solubilities. What happens when a substance is insoluble in water? Again, an aqueous plus an aqueous yielding something insoluble. Then we would expect a precipitate. How can we predict when this will happen? Well, you look at a solubility table. Okay, and you should have done this many, many times. And you can also quantitate the extent to which this can happen, but that would be addressed in a different chemistry course. Okay, so you should review how to predict precipitates. There should be plenty of examples in your book, in your lab, on Blackboard, on videos, all kinds of exercises that you've done in this area. So the next thing that we're going to talk about is a very big concept, and that is concentration units. And there's good news and bad news on this. So I'm going to start with the bad news. The bad news, well, let me back up a little bit. When we were talking about masses, there was only one way to put masses into a stoichiometric calculation, and that was in terms of molar mass. And you looked up molar masses on the periodic table. When we had gases, as long as you were at STP, you could use molar volume, which is 22.4 liters per mole, as long as you had an ideal gas at standard temperature and pressure. And Shazam, you could go about your business with relating gases to the chemical equation. Well, the bad news about solutions is that we have a whole bunch of concentration units. We're going to have percent mass by mass. We're going to have percent mass by volume. We're going to have percent volume by volume. We're going to have molarity. We're going to have molality. And we're going to have normality. So there's 1, 2, 3, 4, 5, 6 different units, whereas before you only had one. Now the good news in terms of this is that it could be worse. We could be doing all 6, but the good news is that we are not going to do normality. And we're not going to do equivalence. Okay, so we're going to do percent mass by mass, percent mass by volume, percent volume by volume, molarity, which should not be new. Okay, molality relates to colligative properties, so this one will probably be new to some of you. All right, page 18. Again, this is a reminder of what we've seen before about molar mass, molar volume, and so forth. All right, so we're going to start with percent mass by mass. And by definition, percent mass by mass is mass of solute in grams divided by mass of solution in grams times 100%. Now remember that solution is both solute and solvent. Solution does not mean water. Solution does not mean water. Okay, so for example, Mountain Dew is not water. Coffee is not water. Beer is not water. Okay? Root beer floats is not water. Okay? Solution is not water. And this is the biggest thing that messed people up. Okay, so you're going to use this when both your solute and solvent are in mass values. All right, what is the mass percent of 40 grams of barium chloride dissolved in 125 grams of water? Percent mass by mass, 40.0 grams divided by 40.0 plus 125 grams. This is your solution times 100% equals 40.0 divided by 165 times 100% is equal to 24.2%. And sometimes your writer will write mass by mass. Okay, let's change the problem. Instead of water, it's going to be solution. Percent mass by mass equals 40.0 divided by 125 times 100% equals 32.0%. Okay, now these look very close, they look very similar, but if you take an error analysis between the two of these, this number minus this number is about 8. 8 divided by 32 is 1/4. 1/4 is 25. This is a 25% difference. Think of it like this. Think of it in terms of getting a 25% pay cut. Is that a difference? Most of us would say yes. Okay? The last one, this is water again. So percent mass by mass, 25.9 grams. Divided by 25.9 plus 178.3 times 100%. 25.9 divided by 204.2 times 100% is 12.7%. Okay, so that's all great and well and good, but sometimes you don't have units that are in mass, and you need a volume percent. So the next segment will begin there.